Alright, this is an attempt at a video lesson. Let's go. So, we're doing a few more things with the derivative today. Hopefully, with your homework last night, you got some practice doing this and you feel a little more comfortable with how to apply it to fairly simple situations. And we're just going to go a little further today and look at the applications of the derivative. First thing is just like basic derivative rules. The derivative of f of x is f prime of x. This is pretty simple. The derivative of 5 times f of x, well, let's do a little investigation here and go, okay, if f of x is x squared, then 5 times f of x would be 5x squared. So I'm just going to take the derivative of these two things and see how they compare. So the derivative of x squared is 2x. I should probably zoom in. And the derivative of 5, so the derivative of this stuff, I guess I'll just write that, is equal to, pull down the 2, and we get 10x to the 1 power. And yeah, it's just times 5 to get from 2x to 10x. So the easy rule is that when we have 5 times f of x, the derivative is just 5 times the derivative of f of x. Hopefully it kind of makes sense that that would be the answer. Our next one, if we just add a number, well, if you remember, the derivative of a number just goes to 0, and so we just get f prime of x. And if we do both, multiply by something and add something, well, this just goes away, and we just get 3 times f prime of x. Writing things in terms of functions and in walking notation is something the AP test is very fond of, and so this is something you have to get used to for that. All right, next thing is the derivative is super useful to find horizontal tangent lines, or where the slope is 0 for a function. That's what horizontal tangent lines are. Notably, these are, if we have some sort of graph, yeah, I know this looks like a sine graph. Horizontal tangent lines happen here and here and here and here. It's basically at our maximums and minimums. And so this is really useful to use, and we're going to be using this throughout the year. And it's pretty easy to do for a lot of the simpler functions that we deal with. So for this first guy, all we do is we take a derivative. So y prime is equal to, pull down the power, 2x, and the number goes away. Now we say, where is that equal to 0? So we say 0 equals 2x, and x equals 0. So it's at 0 that this thing has a horizontal tangent line. That should make sense because you know how to graph this. It's just a shifted up parabola, and that's at 9, and that is where our horizontal tangent line is. So this answer makes sense. Now let's do one where we don't know the answer right away, which is the second guy. It's y is equal to x plus sine x. So our derivative is equal to 1 plus cosine of x. We set this equal to 0 because we want where the slope is 0. So we need to figure out where 1 plus cosine of x equals 0. We subtract 1 from both sides, and we get negative 1 is equal to cosine of x. And then where is cosine of x equal to negative 1? And we're going to have infinite answers to this. But the most obvious one is on our unit circle, where cosine is negative 1 is here. So that's at pi or negative pi. So x is equal to pi is one of our answers, and then all of our other answers are just going to be 2 pi around the circle after this. So it's plus 2 pi times k, where k is all integers, that answer. All right, case you can't see, I'll do a little zoom in here. Yeah, that's my answer. If it just said between 0 and 2 pi, it would have just been this as the answer. But since it didn't have any specifications on this, these are all the points where this thing has a horizontal tangent line. If we want to look at the graph of this real quick, it's some sort of x, but instead of just doing x, it does some sort of like sine-y thing. And it makes sense that we'd have quite a few flat places going on here. Notably there and there and stuff like that. All right. Next concept is matching up tangent lines to graphs. So we're finding where the slopes match and where the functions match. This is the hardest thing that is going to be on tonight's homework. But it's not that bad. So this is our tangent line, and this is our function, and you're trying to see like at what x value these meet. So what you do is you just set your tangent line equation equal to your function equation. Okay, then you set their derivatives equal. So this is the trickier step. So this is functions equal. And the next one is derivatives equal. So our derivative of the first thing is just negative 2x, and our derivative of the second thing is negative 6. Turns out that's really nice. We can just divide by negative 2. We get it that it's at x equals 3 that this happens. Now we can plug that back into our function equation and get k minus 9 equals negative 6 times 3 plus 1. We want to solve for k to figure out like which one of these parabolas actually meets our negative 6x plus 1 line. This is negative 18 plus 1, that's negative 17. And then we just add 9 to both sides, and we get negative 8 is equal to k. And so that is the value of k that's going to make these two functions match up. If we wanted to write the equation of that guy, we'd say f of x is equal to negative 8 minus x squared. And that would be the parabola that has a tangent line that looks like this. So kind of tricky stuff, but very simple steps to get to that answer. Let's go down and get another problem that's like this. So set their functions equal. K root x is equal to x plus 4. Set our derivatives equal. Oh, this derivative's a little tougher. K is just a constant, so I don't just rewrite it when we do our answer. If you remember from the first slide today, when we have a constant multiplied out in front, it just comes with us into the derivative. So no problem there. So k times the derivative of root x is, well, it's x to the 1/2. So it's 1/2 x to the negative 1/2. All right, our derivative on our right side is 1, so that's easy. Now this is a harder case because we don't have just, like, in this one we got rid of k when we took the derivative of both sides, but here not so much. So we're just going to have to solve this equation for k. So I'm going to do that first by, I guess, multiplying both sides by 2, and I get 2 equals k times x to the negative 1/2. And then I'm going to multiply both sides by x to the 1/2. And so if I multiply by x to the 1/2 on this side, it cancels out with this, and it just moves over to this side. So I get 2x to the 1/2 equals k. That means 2 root x equals k. Now I can plug this in to my other equation for k, and I get 2 root x times root x equals x plus 4. That's really nice because root x times root x is just x. And so this is 2x is equal to x plus 4. I subtract x from both sides, and I get that x is equal to 4. So that's our x value at which our tangent line and our function meet. Now the other piece is actually figuring out the k value that we need. And so I have to now plug 4 into one of these equations. I'm going to choose this one because it's simpler. So k times the square root of 4 is equal to 4 plus 4. And so 2k equals 8. Divide both sides by 2, k equals 4. So actually k is also equal to 4. And so our function that has a tangent line of x plus 4, it has it at x equals 4, and the function is 4 root x. So f of x is equal to that. These problems are kind of tricky. If you're really struggling with these still, either come talk to me or wait till next class when I get back, and I'll try to explain it to you then. All right, last concept is about continuity, cusps, and differentiability. So the two things that break differentiability, okay, this word means the derivative is continuous. So you should probably just note that. It's an intimidating looking word, but it has a very simple meaning. Like, if the derivative is continuous, then it is differentiable. So those have the same meaning. And so all we have to do to test for differentiability is, first, is the function continuous? And second, are there any cusps? And that's why I said that these two things are the important things we're testing for. And also why I really want you guys to get your test back and do this test correction thing, learn about continuity, because it's relevant to where we are now too. Here's an example of a cusp. It generally happens in a piecewise function or in an absolute value function or something like that, where the slope instantaneously changes. So going into this point, we have a negative slope, and coming out of this, we have a positive slope. That's an instant change. If you have Mr. Buckley, he tells you cusps don't exist in real life. He's right for the most part. It's more of a theoretical concept, but it's an important one for us to talk about. All right, let's do another quick example of finding differentiability, where something is differentiable. You're going to get homework problems that give you a graph like this, and are going to say, where is this thing differentiable? And you're like, well, totally in between here and here. So on this graph, if I was just saying, from -1 to 6, where is this thing differentiable? I'd first say it's definitely differentiable between -1 and 3. Clearly, we have some sort of problem going on at 3. There's a step discontinuity here. Assuming these line up, it doesn't really look like they do. So maybe this is like 3.1 here. So I'm actually going to say I start my next interval where I'm differentiable at 3.1. And that goes until I get to 4. At 4 here, this slope does not look to me exactly like this slope. It looks like it's instantaneously changing. So I'm actually going to say, I think this is a cusp. I mean, I also think this is a cusp. So we're going to have some more breaks in this thing. So the next interval is from 4 to 6. It's differentiable in between these two. But then it falls apart at those 2 points. If it asks you where this thing is not differentiable, well, we said it didn't exist in between here and here. So this is differentiable. Let's write where it's not differentiable. And I can spell, I promise. All right, it's not differentiable. Well, between 3 and 3.1s, including the edges. Because it's not differentiable at those 2 points, for the same reason it's not continuous. at those 2 points. And then here at our cusp at 4, and at our other cusp at 6. And so if we had to say all the spots where it is indifferentiable, that's how we'd go about saying it. Most of your graphs are going to be simpler. They're going to have like some asymptote, and you're going to be like, it's not differentiable there because it's not continuous. And the only thing you need to check for beyond that is whether or not there are instantaneous rates of changes changing. Like if it changes its slope instantaneously here, that's where you have some sort of like problem in a cusp. All right, 15 minutes is way too long for a video, but hopefully you learned something.